G'day viewers, welcome to my happy place. Dogs, jooks and guitars. Let's go in and see what we're doing today. G'day viewers. Today's episode is about this Frankenstein looking jig that I made for the purposes of measuring bridge rotation in an unknown quantity soundboard. If you've made 5 guitars out of a similar soundboard material, then you pretty much know what works and what doesn't work. But when you've mixed up the soundboard to something you've never used before, it's difficult to know what sort of bracing is required to ensure that you've still got an active soundboard. As a mother of invention, necessity required me to do so. When I made this, which is a sapwood soundboard, which I've never done before, and it was full of boreholes, and it actually took a bit of resin filling to ensure that it was going to come up fairly soundly, but I wasn't sure once under string tension what sort of activity the soundboard would offer. So I came up with Mr. Frankenstein here. Just show you it's a nice unit, sounds good. It is an X brace though. So what I've been doing more recently is valcate bracing, which offers a number of benefits, and it's proposed by Gillette and Gore, Australian guys who make a lot of guitars and who I rate fairly highly. Anyway, so the idea of this jig is simple but effective. So the way this sucker works is pretty simple. I've got a 300mm ruler. The difficulty I had was that there was about an inch on the end with an eyelet in it, obviously, to hang it up, which what happened was that caused it to be out of balance. So I chopped that component off the end, so it's 0 to 300. And the fulcrum point is at 150. So what you can do then is calculate based on the proximity of these points here against the vertical rule to determine the degree of the millimeters of movement, and then from that calculate the degree of movement using sine -1 function on your calculator, which I can't show you at the moment, but because I'm filming with the camera with my phone. So why is bridge rotation so important, in my mind anyway? Well, I'll let the experts brief you on that, and those being Gore and Gillette from Australia, who proposed that at 3-8, without disclosing too much copyright here. We have found that a good balance between the allowable angular deflection and the longevity of the guitar is achieved when the angular rotation of the bridge under the tension of the strings is not allowed to exceed 2 degrees. So the maximum allowable rotation of the bridge under full stress of the strings is no more than 2 degrees. Now, why? Well, let me go on. Much greater than this, 2 degrees, the guitar top takes on a permanent deformation even with the load is removed. So that's where you get a belly in the soundboard. Much less than this, much less than 2 degrees, and the guitar top will not produce sufficient volume. Now, that's what it's about for me, is making sure I'm getting the most volume out of this guitar, based on the strength of the bracing against the tension of the full strings. And you use the sine rule, sine -1 rule, to determine that. So in my case, where I've got 150mm fulcrum, if it moves 5mm up and down when the string tension is in place, then sine -1, 5/150, comes to 1.9 degrees. So that's the magic number, according to Gore and Gillette. Set this up. In this case, as in this demonstration, using this Bunya Pine soundboard, which I have used before, but I haven't used with a falcate bracing before. So I'm keen to get an empirical measurement as to what the bridge rotation will be once the bracing is in, and then I can manipulate it or voice it to ensure that I only get the 2 degree rotation that I want, or I get at least 2 degrees, but not more, say 1.9, yeah? So again, this demonstration, I've got 3 strings set up. I've got the 53 thou E string, near as, a 32 thou A string, tuned to pitch, and a 24 thou G string. I'll then adjust this happy little fellow here to be right on the point. And then dump the string tension by turning this turnbuckle. So if we just watch that point there, and dumping string tension now, it's 1 turn, it's 2 turns, that's 3 turns, 4 turns, and that's loose. That is actually about 6-7 mil. So that's a lot, that's too much. Just with 3 strings. So imagine how it would be if I had all 6 strings tensioned up. I would pretty well burst that soundboard. The reason being is I have no bracing whatsoever at the moment, because this is my base point. I'm just setting this up whilst I have the hole reinforcement plate and the bridge plate in place. Those 2 bolts obviously hold the bridge down, and I've used a pinless mechanism for the 6th string and the 1st string to allow me to use the 1st and 6th string holes to bolt it down, so I don't have to cut any more holes through the soundboard than is necessary. Obviously I've made sure that I'm in the right position based on the 14th fret for intonation purposes. So using the Diodario data for a set of 12 thou to 53 thou strings tuned to pitch, you'd expect 176 pounds tension for the full set, whereas I'm only using the E, the A and the G, which comes to say 95 pounds. So I'm still a fair way off the full. But interestingly, that I did get the rotation out of 3 strings that I'm probably looking for. So that's the explanation of how this is going to work, and what I propose to do going forward is create the soundboard using the bracing that I propose, which is the falcate bracing, and measure it at each interval the deflection of the bridge, and that way when I get to the final bracing configuration, I will know that when it goes in the box, I will actually get the right amount of deflection on that bridge, and therefore the maximum amount of movement in the soundboard, and therefore the maximum amount of volume. Thank you very much.